So just a quick reminder, presentations are going to be next week. So now I promised you guys like a quick Google Forms to do if you want to do in-person or recorded. I will make sure to do that by the end of the day. Yeah, but to make sure everyone is kind of on the same equal footing, like everything is going to be due, the presentations are all going to be due on Monday by class time. So you have to get your presentations in by then, and if you're going to do a recording, then you have to get those in by then as well. And those assignments will happen soon. Any questions about final project presentations? We'll just be, either submitting the recorded one or in class next week. Okay. Okay. Today we're going to start with a quick quiz. Not really a quiz, but here are two pictures. Can anyone tell me what this picture is on the left?
A cat.
A cat? How the hell do you guys know that this is a cat? What about on the right? A dog. Very interesting. Very interesting. Okay, so you guys picked up on that very easily. But like, what is it? What are the features about this image that we're like, that's a cat, or that's a dog, right? You know, this is not the same, picture of something that we would see in real life, right? It's super blurry, and yet we are still able to do this kind of task of classification, right? So there's something about this picture that's leading you to believe that that's a cat. And we could do this kind of exercise for other sorts of blurriness or other sorts of sort of interpolations of the pictures, right? So these are the same pictures filtered in a slightly different way, right? And then here are black and white pictures, and yet you guys would all probably have been able to identify cat and dog, right? So from your original picture. Actually, I guess let me ask you guys, what features of these variety of pictures are leading you to come to that conclusion? Yeah. Okay. So the shape of it, yeah.
I guess for me it's more like I've seen dogs and cats before, so I can relate.
Yeah.
I've never seen a dog or a cat before.
Yeah. Okay. Great. So actually, that's a really good answer. And so with the shape thing, yes. So that is, I think, what you might be sort of latching onto there. But like, consider that I could show you maybe like a part of a cat, and maybe you'd be able to tell, right? So like if I showed you the eyes and the nose, maybe you'd be able to tell. Or if I just showed you one of the ears. So it is shape, but it's like, shape is one feature amongst a culmination of like experience that you have had, right? You just see a bunch of these things and you're like, oh yeah, I've seen a cat before. That must be a cat. And that's kind of how these machine learning algorithms are kind of working, right? So when we do these classification tasks, right, it's not pictures. We haven't talked about pictures yet, right? But it's like, you see some feature set, a whole bunch of different attributes, and then the model is like classifying based off of its experience of knowing that, hey, that's a cat and that's a dog. And so, in a very similar way to the way our brains work, where we kind of store this experience information, we're going to try and do that today with neural networks and images. And so this is another example where I guess the idea is that I can specifically manipulate images to provide a sort of simplified version of a picture that will be easier to translate into like numbers in some way. And so today we're gonna kind of build off of the neural network stuff that we covered last time and try and shed a little bit of light into what's going on behind the scenes when we think about doing classifications of images. That'll be kind of like the first half of today, and then the rest of it we'll do like the overview of the content in this class. Because today is actually our last lecture. So, okay, any questions about any of this stuff? Okay, great. So let me get out of here and let's talk about convolutional neural networks, which is, they're called CNNs. It is a subset of a broader set of neural network models. So convolutional neural network, class of deep neural networks. This is a regularized version of multi-layer perceptron. So this is particularly suited to analyzing grids of data. Especially for classification. All right. So consider, all right, I'm going to draw a very simple picture. Okay, what is this? Yes, okay. I still got it. All right, so how on earth are we gonna feed this into a neural network? So we've always been so far just like feeding in like numbers, right? Or kind of discrete variables that relate to some kind of like larger feature set. So what would we do here? Anyone have any ideas? Okay, so when you have a digital picture, does anyone know what this is comprised of?
Pixels.
Yeah, and kind of more specifically, inside of an individual pixel, what is being represented? Color, exactly. And so on a digital medium, it's represented in a combination of 3 colors, right? You guys have probably heard of this. So RGB, so red, green, and blue. And you can have values to represent the intensity of each of those colors. And when you mix these things in different combinations, you get different colors. So I can actually separate this out into, right, individual pixels of red, green, and blue, and so on and so forth. Right, and so these will have numbers inside of them, 57, 83, 5, 62, whatever, okay? And so now we're cooking, right? This is like, we're in the number territory, so now we can start to deal with this in certain ways. So why not just like take this information and just like feed it straight into a neural network? Does anyone have any ideas, right? We talked about how you have like inputs, right, that go into a neural network. And why not just take that and put it in? Any like lurking suspicions? So it turns out that even for fairly small images, like consider how many pixels that you would need to represent this, right? And so this would be too many weights for a multi-layer perceptron. So you wouldn't necessarily just take a raw image, separate it out into the RGBs, and plug it into the neural network, because usually that's like too big. There's too many nodes. The computational complexity of like processing all of that is too high. However, do we need all that information to do a good classification, right? So you guys looked at a bunch of examples just now where we had a lot of like image quality loss, or we were looking at like edges, right? Where that information still allows you to do classification effectively. And in a similar way, you know, instead of looking at a bunch of pictures of cats, I could look at a bunch of pictures of cat outlines, and I would probably still be able to tell that it's a cat. And so what is really common in these approaches, these convolutional neural networks, to process images, to essentially pre-process them before we kind of feed them into these neural networks. Okay, so we will process images with 3 techniques. So 1, convolutional layer, 2, pooling layer. This is a convolution process. And then 3, the fully connected layer. Okay. So the way this works is I can take an image defined by a grid of numbers, right, which is like the RGB values, and I can conduct some kind of filtering process or a kernel process, they're called filters or kernels, on them to achieve specific outcomes. So I'm going to draw one out really quick. And let's see if you guys can kind of identify what's going on here. Okay. So this might be a small grid of a small grid representing an image. Okay, I actually need to write these numbers down. So each of these values might represent like a pixel. Sorry, this is a little tedious. Okay, so times, we're going to have our filter or our kernel here. And these are all going to be a 1. And this will be going to a 3 by 3. Six, 8, 45.7, 58, 63.8, 62.1. Okay. Who magically knows what's going on here? Any ideas? What if I do this?
You're averaging every 9 grouping.
Yes, exactly. That's exactly right. So this process is a filter that averages these 9 things. So this is, when you do a particular process, we do a stride. So this is number of steps in a direction. So what's the stride of this particular process?
9.
Yeah, so so actually we're going 1, 2, 3, and then in that direction, and 3 down in this direction, because I can apply this particular filter across this whole thing. Okay. Before I tell you the name of this particular filter, can anyone kind of guess what's going on here? So if you think of these numbers as colors in an image, and I'm taking the average of zones of the image, what do you guys think happens? Yes, exactly. So this is known as a mean blur filter / kernel. That's exactly right. So imagine if you have like black and then white, and then if you average them, it becomes gray. And so you're blurring out the fidelity of the image. So not only that, so image is blurrier, right? We went from a 5 by 5 to a 3 by 3. It doesn't have to, you don't have to make it smaller. So there's a process called padding where you can add back in essentially piece around it, and so that it retains the same size. But yes, generally speaking, when you apply a mean blur filter or kernel, you are blurring images. Okay, so this is a process that a pretty simple process that we can take, right, that will essentially take an image and make it blurrier. This is essentially how it's done. Okay? Any questions about this? Right, and so again, the idea here is we're trying to simplify the image to reduce the size and complexity to make it easier for a neural network to process. And we know that losing fidelity in the image quality doesn't necessarily mean we lose ability to do classification. Okay, so other types of filters. So let's look at edge filters. Okay, so here is an example of something called a vertical edge filter. So this is vertical. So imagine that I have let's see here, something like this. Okay, and let's say these are all 10s and these are all 0s. The number doesn't actually matter here, but really quickly. All right. So visualize this picture here. It's like you have one color here and you have one color here. So this might be like the body of the cat, and then this might be like the background. Let's say this is like the sky or something, okay? So let's say you have like black cat body here, and then sky over here. So if I take this edge filter and I apply it to here, what you get out of this is something that looks like this. 0, 0, 0, 0, 30, 30, 30. Okay. So I've transformed essentially cat body and sky into nothing, nothing, and then a line. So I've created an edge based off of differences in colors. Okay? So edge filter creates an outline. So that's a vertical. Obviously there's also a horizontal. 1, 1, 1. We also have other types of filters. This is a commonly used one. It's called a Sobel filter. And you have a Okay, and so these are all edge filters of different kinds. They do kind of, they all are essentially extracting edges out of your images in slightly different ways. But yeah, these will all extract edges from your images. Okay, any questions? So we don't necessarily need to know all of the details behind all of these things, but this is, again, just to shine a light into kind of understanding what's behind the scenes in terms of image processing as we prepare it for analysis in a neural network. Yes?
What's the purpose of silver and sharp?
There are different types of edge filters. Yeah. They're better suited to handle certain types of images. Yeah. Other ones, these are not edge filters, but common ones to know about. So in the same way that I can blur an image, I can also sharpen an image. So this is a sharpen filter. And then there is a more commonly used one for blurring called a Gaussian blur. So these filters are actually one of your transformation steps in a neural network. And so we talk about this, right? A W times X, right? And so these are the weights, right? What we used to think of as betas. And this is our input, and this is our activation function. So actually in a convolutional neural network, these are going to be your filters. So the weights are these set filters that are applied to them to transform the data, and then later on we'll have weights that you can actually sort of calibrate. And I'll mention the activation function. We talked about this last time. Most of the cases here are going to use ReLU. Again, as a reminder, this is to help with computation of the gradients. Okay, so if you guys remember, I was talking about the three sort of process steps. So the application of the filter is in the convolutional layer. Then the next part of it, called pooling. I guess I'll go over here. So pooling looks something like this. So pooling is the thing that's really meant to help reduce the size of the image. And so you might apply filters first to blur it or to just create the edges and that sort of thing. And then you would apply this pooling technique to reduce the overall size. So the things you need to think about are the filter size, the stride, and then the max or average pooling. Okay, so who can tell me what the filter size of this pooling would be? Four, right? Okay, so it's a 2x2, right? And then we're applying that to this thing, this thing, this thing, and this thing. So what would the stride be? 2, that's right, because we're taking 2 steps for each filter. And then are we doing max or average pooling? Max. Yeah, exactly. So to kind of decipher what's going on here, so that's our filter size, and then each time we're applying it with a stride 2, so we walk over 2 steps, and we walk down 2 steps, and then we walk over 2 steps, and then we are doing max pooling because you take the largest number here, plug that in there, largest number here, put that here, largest number here, and here. Okay? So this is really going to reduce your image quality a lot, right? You're like conglomerating the pixels into a much smaller subset. And you need to do this again, right, to reduce the computational complexity of your network. Okay, last step is flattening. Converts last convolutional layer into a one-dimensional neural network layer. And just as a reminder, again, we're not doing a fully connected amongst all the layers because a number of weights grows exponentially with the number of pixels, and you have too many parameters to like feasibly compute. Okay? So let's consider a 32 by 32 pixel image with RGB channels. So convolution layer, let's say we have 5 filters, 1 stride, pooling layer, let's do 2 filters, 2 stride, okay, so just the first input layer and Okay, so let's consider each individual number in the grid could be represented as like a single node in your neural network. How many nodes would our first input have? So 32 by 32 pixel image with RGB channels. How many nodes would that be? You don't actually have to like calculate it, but you can tell me the numbers. Okay, 32 by 32, right? So it's that number of pixels times what? 3, right? Because we have a red layer, a green layer, and a blue layer. So you have 3 32 by 32 grids, and that could be, yeah, the sort of number of nodes that you might have there. Okay. So in the first convolution layer, if you do 5 different filters, one stride, remember that as you apply these filters, we're actually going to decrease in size each time. And so with five filters, one stride, you're going to end up with 28 by 28 by 6. Why is it by 6? So 28 by 28 because your image size is reduced, and then you would have 5 filters. So I thought it would have been 5. Why did I write 6 here? Okay, I think this is actually not right. One stride reduces edge on each side, so I think this is actually going to be 30 by 30, and then with one filter each, so it'd be 30 by 30 by 5. Okay, so this is approximately on the order of like 10e to the 7. Okay. So this means you're on the order of like 10 to 20 million nodes-ish in that sort of ballpark. So it gets quite large quite quickly. So you wouldn't want to you wouldn't just like take the pixels and throw them into like a gigantic neural network. Instead, right, in the convolutional neural network, we can think about our input layer, 32 by 32 by 3. We pre-process 5 filters, 1 stride. This is going to be processed down to 30 by 30 by 5. So this is first convolution layer plus ReLU transformation. Then we do our pooling layer, 2F, 2S. This is going to end up being a 15 by 15 by 10 first pooling layer. And then you might have other processes. And the whole idea is eventually we're getting smaller and smaller, right? So we started with 32 by 32 times 3 into 30 by 30 by 5 into 15 by 15 by 10. And eventually you'll get to a point where it gets small enough and then we flatten it. So now we do have a whole bunch of nodes here, but this might be, something like 400 nodes. And then you could have hidden layers, maybe you could have like 100. And then this goes to your, this is like softmax. So this is your end classification on the other side. And oftentimes this softmax thing, so I'll write out the equation, but don't need to worry too much about this. So fj z equals e zj sum k zk. So this is actually a generalization of the logistic function. Okay. I feel like this is kind of a lot to take in, but the main takeaway here isn't anything really complicated, right? We're still dealing with a neural network where you have nodes, you have hidden nodes, you go to an outcome that's a classification problem instead of, the continuous ones that we were doing last time, right? But all this is doing is it's saying you have a whole bunch of preceding steps that translate your image into something that we can digest. And the whole point of this is like that image translation, yes, it's making the image smaller, it's like processing it in certain ways, it's blurring it, it's giving it an outline. But this harkens back to the exercise we did right at the start of class, where you guys were able to identify a picture of a cat and a dog without having like all of the image fidelity that we think you might need to do the classification. And it's the same thing here, right? We can process the image to simplify it and still get good classification qualities. And that's the strength of the convolutional neural network is essentially doing this sort of simplification process to get us to a point where we can feasibly compute a neural network. Okay? Yes?
Is this a kind of model used like for AI when they were doing identification with pictures
Yes.
and the one
It's,
was white kind of thing?
yeah.
How do you know when it's too much to homogenize an image?
Yes, so image classification is, if you're doing image classification in machine learning, it's almost certainly going to be a convolutional neural network. Okay.
So where does the bias come in and how can you avoid it?
When does what?
Like a bias come in?
Yeah. So bias means that I'm systematically making errors in my sort of prediction. So that might be there. Okay, so there's a couple reasons for why this might be, right? So you have a bunch of images of cats and dogs, and you are systematically misidentifying dogs as cats or vice versa. And that could be because of the choice of filters that you're doing is leading to an inability for the neural network to differentiate between the two. And so you might want to like change filters and that sort of thing. But I would really think of this as analogous to the way that we as humans will classify things. If I'm misidentifying like an animal species or something, maybe I just don't have the right amount of experience. Maybe I'm viewing it in like a non-ideal way. And so these are kind of factors that you would think about when you're processing images computationally as well. Okay, so there's no one solution to like fixing bias in some of these models, but there's a lot of things that you can think about to fix some of those issues.
The main one being filters. The choice of
No,
filters.
well, that's just one example. It could be that, but it could be any number of things. Like, you know, if all the classifications were on the ears of dogs and cats, maybe you should like get more pictures to have more training. You should like expose the machine to other body parts of the animals, right? So it's, you know, it could be any number of things. But you can think of it as analogous to the way that we classify things through experience, right? Okay, so I'm gonna just copy and paste a whole bunch of code here. Not really meant to follow along, but you guys can have this as reference. And part of the reason is because we actually need a special installation thing, which actually takes a little bit of time maybe to set up. So if people are interested in doing this, I'm happy to help with that, but you need to install some other stuff first. So just kind of enjoy the ride. So TensorFlow, Keras, and Purr. So TensorFlow and Keras are both machine learning tools very commonly used in the machine learning community in both Python and in R. And then we're using a pretty well-known data set called, I don't actually know how to pronounce it. I don't think I've ever heard anyone pronounce it, but CFAR, I guess. So let me show you what this looks like. Here we go. So these are 30 images. They are pretty low resolution, okay, because how big are these? These are, I think they're 24 by 24 pixels. I'm actually kind of blanking on it, but low quality images, right, so that we can speed up kind of the processing of these things. Okay, and you got a bunch of different images. We have airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. So if you guys look at these images, what do you think they are? So 1, frog, 2, yeah, or automobile, I guess. Oh, sorry, 2 is going that way, not that way. Yeah, you're right. Truck, 3, truck. This is a deer. It's so much harder from up close. It looks so clear on this small monitor, but when I turn it on, I'm like, what the hell is this? Deer, car, bird? I think that's a bird. I think it's like an ostrich or something
Oh,
like
it's a
that.
cassowary.
It's a what?
It's a cassowary.
Cassowary, yes. Oh yes, very obvious. Horse, ship, cat, deer, horse, bird, truck, cat, bird, frog, deer, cat, frog. Frog or bird?
24
Oh, okay. It actually looks better on the screen now. 24 is a frog, bird, frog, cat. Is that a dog? Yeah, dog is one of them. I think that's our first dog. That's a moose, but I guess we're gonna call it a deer. And then an airplane. Okay, so with our human eyes, we have been able to classify these, and let me see if we can apply the neural network and see what happens. Okay. Ooh, I haven't done this on this computer yet. I hope it works. Yeah, so it's got a bunch of trainable parameters, which are basically the pixels, right? So actually, let me see. So I can tell you how many pixels because I can do this. 320 divided by 3, and then, wait a minute. Oh, it's doing some, okay, sorry. It should be this approximately the square root of this number. No, that's bigger than I thought. So okay, so it's already doing some filtering at this point. Okay, so we flatten it. And running this actually will take a while. It's using this TensorFlow. And remember, with a neural network, there's some there's some iteration, right? Because the weights have to be calibrated so that as I update the weights, I am taking a step in a direction that improves my mean squared error. In this case, it is reducing the error of the classification. And as it steps through each of these epochs, which is a version of an iteration where it's updating the weights, we can see that the accuracy of the model is increasing up to a certain point. It should generally continue to increase every time. And so accuracy is telling us in a training, in a testing set, how many I would be sort of guessing right on average. So this might be doing some kind of cross-validation thing, right? And so, up at close to the limits for the number of epochs that we're specifying, it's getting about 2/3 of the classifications correctly. Okay. Where's the bottom? Yep, so this is just the same thing we were seeing. Yeah. Okay, and so with the final model, it's doing, it has an accuracy of about 2/3. So on the testing set, we've just trained a neural network that you can pass in images of low quality of different, airplanes, automobiles, birds, cats, deer, and so on. You can pass any image to it and it'll get it right about 2/3 of the time. Okay? So, yeah, the implementation of this, not going to go through this in detail. If folks are interested in learning more about CNNs, walk through the code, and I'm happy to help sort of review it. But it's there and available for you guys. But this is just to show, again, right, kind of cool that we created this model that can essentially interpret images of amongst these, I think, 10 categories of objects. Okay, great. Any questions about CNNs? All right. In that case, let's jump over. And okay, we are going to transition to, yeah, let's do a kind of quick overview. I like to kind of give this lecture or this piece of lecture at the end of the class to kind of back us out, think about all of the material that we've covered, how it relates to each other, and kind of more sort of principles to think about when you're doing data analysis. So there is a large component of this, which is like developing these models to analyze the data, right? But one thing the number one thing, even before you do any of that, which maybe we didn't spend as much time talking about in class, but hopefully you guys had some direct practice in doing this in the homeworks, is really just to examine the data. So investigate the distribution of data, look at basic relationships between variables. And this is kind of tricky. A lot of what we're doing is to understand relationships between variables in a sort of deeper way. And so looking at kind of basic correlations and that sort of thing can be useful. Just be wary that there's some underlying things that might be difficult to extract out of simple like correlations and that sort of thing, which is not to say that you shouldn't do this, but this is kind of like a step one, right? And then you want to develop hypotheses about the data. So looking at the data can help you develop some hypotheses, but you can also go into the data having some hypotheses ready to go and sort of thinking about how to measure relationships. But either way, when you examine the data, you might want to like update those hypotheses that you're coming into it with. Okay, so that's kind of like prior stuff to even conducting any analysis. Like oftentimes it's very common for me to like work with students where they'll get like a data set and then they're just going to jump into like start running these regressions. But that's something that you really should do after you kind of look through the data a little bit deeper in a more sort of summary way, rather than just like jumping in and starting to run regressions right away. Take some time to like look and understand the nuances of the data. Okay. So then number 2 would be then to develop some model / learn from the data. Okay. I guess I kind of did a but we're really going to divide the analyses that you do on the data into supervised learning and unsupervised learning. And actually last time during the lecture I misspoke and I wrote, I misspoke and I wrote down here explanatory variable and no explanatory variable, but what I meant to say was, I think everyone has understood, right? No, so response variable, aka y, or no response variable, aka no y. So this would be our clustering, and then we never really got to this topic, but dimension reduction. So this might be stuff like PCA, factorization. And here we did linear regression as our kind of simplest mode, and logistic regression for our simplest mode for continuous and discrete. And we had kind of a progression of more complicated regression types in the continuous area, and so can anyone help refresh my memory on what some of these things were?
Time series?
Time series, okay, yeah. So I'm gonna like kind of put that off to the side, time series. But you know, we talked about like less complex, the more complex models. Yeah, exactly. So we had polynomial, we looked at stepwise, and then we went to splines, exactly. And then kind of a alternate path, kernels, right? And then eventually to neural networks. And similarly, on the discrete side of things, we talked about sort of non-parametric. So this is kind of like the analog of the kernel. So this might be K and N. But there's, you know, other things, LDA, and then eventually our neural networks as well. And actually, maybe in between neural networks, we might do the, what is it called? The support vector machine, or the ones before that. The other ones with support vectors. I'm totally blanking on the names right now. And then into neural networks. Okay, that's kind of our sort of high level in terms of like evolution of less complex to more complex. And then, you know, we have data sets with many variables, x1, x2, x3, x4, so on and so forth to xn. So how do we, sorry.
So questions, could you lower it a little bit so I can take a picture? Please?
Oh, sure.
So I couldn't open the file. And the other is LDA is for normal distribution data.
Yeah, most ideal for that, normally distributed. Yes. Okay. So for any one of these models, we may have lots of different variables that we might want to put into our regression. And so how do we know which variables make sense to put in?
Rage and lasso.
Range and lasso is, yes, one of the forms. So there are variable selection techniques, right? And so I'm actually gonna, okay, 1, 2, 3. So ridge and lasso are a form of regularization. So ridge, lasso, and elastic net. What's number 1? Anyone remember? Stepwise, yeah, exactly. So this is subset selection, and so this might be stepwise. Okay, number 3, we again didn't really cover this dimension reduction, but you can do that to help isolate the contribution of individual variables as well. But okay, put that aside. I think 1 and 2 are probably more common for this type of stuff. Okay. So linear regression. Relationship is linear in parameters. So we have something like y equals beta 1 x1 plus beta 2 x2, so on and so forth, beta n xn. And what about diagnostics? What are the things that we look for to tell us information about how good a model is or how good aspects of the model are?
R squared.
R squared. I heard MSE. What else?
The statistical significance.
Yep, significance. Okay. Anything else we should be thinking about?
AIC.
Okay, yeah, so AIC, BIC, yeah. What else would I ask you to look for with models, with any sort of regression model? Okay, FSTAT. I probably wouldn't ask you to look at an FSTAT, but yes, it is a diagnostic measure. A shitty one. Okay. There's one big one that I've kind of emphasized before. Sorry? RMSE, I would consider that kind of like in the same vein as this. I'll give you a hint. It's not all of these are like numeric things that you could just look at. And the one that I'm actually telling you guys that's missing is not a quantitative metric. It's a visual metric. Residuals, yes. Okay, I'm gonna like super underline this and circle this. Because you guys are, yeah, outliers would be, we could look at outliers for part of the diagnostics, yeah, and so we have Cook's distance, we have leverage, yeah. But that's like the very easy one to forget to do, as we can just tell. But don't forget that one is one of the most important ones. It is the one that is most able to consistently inform you about bias in your model. none of these other ones will do that. And residuals is a really, really powerful way to be able to tell that your model is biased. Okay. Logistic, regression. So this is where our response variable y is categorical. And the whole point is a logit transformation makes this into a continuous outcome. And the whole point of the logistic regression outcome, right, is you have different categorical outcomes. So you might have, like, instead of a continuous set of numbers, you might have dog, cat, chicken as your outcomes. And the logistic regression is the sort of power of the logistic regression is it tells you what. So if this is, you guys remember this logistic curve over some x value. What is the y-axis here? Huh? What? Oh yeah. I think I'm like mishearing you, but odds. Yes. Yeah. That's right. It's this plot is not. This particular plot is not the like odds or log odds. I'm actually just graphing a transformation of those into a probability. But yes, but the idea that's the correct sort of intuition here is that I'm now telling you the probability that the outcome is a dog or cat or chicken, right, or whatever discrete value. Yes. So that's logistic regression, and we're approaching the analysis of this in a very different way from linear regression, right? Because our response variable is fundamentally different. Okay, and both of these eventually swing into semi-parametric or non-parametric territory, right? This is kind of where we move towards the latter half of the class, right? And this is having to do with the fact that, if I have some set of data, right, am I fitting a line to it? Is it non-linear, right? And so even if you suspect, right, or that you want to do a linear regression, you ought to still be checking that the functional fit between your data is actually linear. So this is a good check to do some kind of semi-parametric or non-parametric model, even if you're intending just to run like a linear regression. It's always good to at least check the linearity assumption. Yeah.
everything can be kind of simplified into linear. In
So,
the value of, yeah, can you repeat the last concept?
so I'm gonna touch on this topic in a little bit more detail in a second, but this is a thing that I've been trying to emphasize throughout the class, right, which is, or the design of the model is meant to facilitate it's meant to facilitate a particular outcome that we are trying to do. And generally, I've kind of divided that into two worlds, right, where we think about like predictive outcomes and causal and inference type of outcomes. And so prediction, right, is just where I want to take inputs and be able to give the most accurate response value as possible. So I want to be able to predict y's given some x's to the highest sort of accuracy and precision. And that is much more in the world of semi-parametric and non-parametric. Okay. The other side of the coin is in the sort of causal land, where I really care about understanding how x's relate to y's. I may not even care very much about how good I can predict y, as long as I'm understanding a particular effect well, you know, whatever effect that I'm really sort of interested in. So, okay, let me see if I can come up with a good example here. So maybe based off of an earlier example that I talked about on the causal side. So if I wanted to understand how much someone is going to drive in a particular day, and I build out a really complicated model, and I understand things about their schedule and the weather and like gas price and all of these things, and I can very sort of accurately say, oh, they're going to drive like 30 miles a day or 50 miles a day. That is something where I care a lot about that outcome prediction of guessing that many miles. And then conversely, in this example, maybe I really want to understand the effect of gas prices on the amount that this person drives. And so I really focus a lot of the analysis on the inference that I can make from that. So essentially that like beta value associated with like a gas price, you really want to hone in on that, even if things about their weather and commute and occupation are like inaccurate in producing a good prediction, as long as I fundamentally establish a good relationship and understand the relationship between like gas price and that outcome, you know, that's a very different sort of model. And in that case, we really care about like more interpretive aspects of the model, and so oftentimes inference is focused more on like more simple like linear type regressions where you can retain interpretability as opposed to these other models. Does that make sense?
Interpretability, parametric or semi-parametric, predicted, given inputs, while the accuracy of an outcome. The other is
Yes,
causal.
that's exactly right.
X is related to y's with respect to one effect, depending on one variable and how it impacts loading.
Yes. Yeah. Okay. So, what do we talk about with this stuff? And even more extreme, like different fits of models. This is one of the more important principles of this class is how we increase model complexity will always give us better fits to the data and reduce what? Does anyone remember?
Interpretability.
No, this is a very specific aspect of error. What are my components of error? There's 3 pieces. Bias, variance, and then, does everyone remember the last one we talked about? It's 3 components of error: bias, variance, and noise. So noise we kind of ignore because you can't really do anything about that. But how does bias vary as a function of model complexity?
Decreases.
Yeah. So we have something like this, and then this goes up. That's variance, and our total error. This is just error. This is total error. And anytime we are trying to build a model, and we have the ability, right, to add complexity into the model, or reduce complexity into the model, we're always aiming for this kind of sweet spot here, the lowest point. And how do we do that? Cross-validation, yes. It's the last time I'm going to ask you this question. But yes, cross-validation, right? So it's very difficult to theoretically be able to hit that point, that sweet spot every time. So we just do it empirically, right? Run a bunch of different models in a smart way until you get to this lowest point here. And we've explored many different ways of increasing or reducing model complexity, right? This goes anywhere from more variables. Adding more variables increases model complexity. Choosing the right number of variables, a la subset selection, right, a la stepwise, is how we get there. In Ridge and Lasso, we get there by the tuning parameter, right? If you allow for all the variables to be in there and allow them to contribute to their fullest extent, that is that side of model complexity. And as you increase the tuning parameter, you give a larger penalty, and it's going to slide back down by regularizing the coefficients in your model, right? Polynomial regression, you can add more polynomial terms. Stepwise regression, you can add breakpoints with splines. You can add knots with smoothing splines. You can change the tuning parameter, right? So we've covered so many of these things, but fundamentally it's all connected to this in principle, okay? It's all about getting to the sweet spot, and we do cross-validation across these many things that you can vary to be able to get there, okay? And then for causality, we think about using DAGs or directed acyclic graphs in order to understand relationships between variables and what we need to do to extract causal outcomes based on hypotheses about the relationship between variables. And DAGs is a really good way to kind of visualize and understand what you need to manipulate or include in certain ways in the model to make sure that you're getting to inferential and true sort of causal outcomes. We talked about a handful of tools that help us achieve what the DAGs essentially are telling us to do. Does anyone remember those tools? There's 3 of them.
SEM.
No, that's for classification. That's actually, yeah, more on the predictive side, not for causal. Anyone? How would you try and do causal inference? What are some models that we could use? Okay, so the first one is fixed effects, right? If you guys remember, it allows us to take advantage of panel data in a unique way that eliminates the need for a huge number of variables that you might otherwise need to include to be able to do inference, right? And so, yeah, if I have a treatment effect that gets applied to a random set of people, it might be difficult to distinguish those effects across different people because they're all living different lives and there's lots of variables that you might have to control for to understand the effect of the treatment. But suppose instead you were to follow one person over time and observe changes that happen as a result of a treatment. In that case, you're kind of doing and you do that across many different people and track them in a before after type thing. In that case, right, we are essentially looking at the changes within the panel of within an individual person, which then allows us to eliminate all of these other controls that you might have needed to control for. So fixed effects is a very powerful way to do inference. Differences and differences. Similar type of thing where we observe specific points in treatments and see what happens before and after. Actually, the example that I gave is a subset of differences and differences of fixed effects. It's a two-way fixed effects with differences and differences. So there's some overlap between 1 and 2, but hopefully you guys get the idea here. And then the last one, anyone remember what the last one would be?
Instrumental.
Yes, thank you. Instrumental variable regression. Yes. Causal stuff, very tricky to do correctly. Yeah, there's a lot of work in this area to think about causality. It's kind of a different spectrum of analysis that we're doing, but hopefully in this class you're kind of getting a little sampling of both sides of the coin here, right? Both on the predictive outcome side and a bit on the sort of inferential side. Okay, so that is kind of number 2. And lastly, number 3, sort of interpreting and contextualizing your results. So what do the stats say? And what do they not say? Yeah. So yeah, this can be frustrating at times actually, like the level of confidence that people have in interpreting models and how good models are. Like just the other day, there was a more senior researcher who was like, oh yeah, like don't listen to the model, this model, it's got like a bad R-squared. It's like, okay, like the R-squared might be low, but that means something, right? We know an interpretation of an R-squared as like, okay, if it's a low R-squared, the variability in the model, a lot of the variability might not be captured, right? But there are lots of other things to think about, right? That is like one aspect of a model diagnostic. And you guys should hopefully walk out of this class with a tool set to not be so general about these things and to really have a good sense of what our particular interpretation of any individual diagnostic means, right? So where did I write all this stuff? Like when people talk about significance or R-squared, right? There's all these other things that you ought to be thinking about holistically to think about the quality of a model and interpreting what it means. And so just be careful about this like interpretation part because that's really important. Yeah.
The two big buckets that you're teaching us,
Yes.
should we focus on different diagnostics for each, or prioritize?
So what buckets are you talking about?
Prediction and
Ah.
probability?
Yeah. Actually, yeah, that's a good question. So, generally, I'm going to say there is a bigger focus on certain diagnostics tools in prediction versus in inference. And that's fine, but you should still be thinking about these kind of holistically when considering kind of overall quality. And so in inference, I might really care about like significance of variables if you are focused on understanding effects of treatment, right? And so if the treatment is like not significant, that's like kind of what you were striving for, right? Is to understand how a treatment effect relates to an outcome, and so if it's not significant, that like means something sort of fundamentally important to you. That might be less important in prediction, where any individual significance is good, may not necessarily be good or bad. It's all about making sure your outcome predictions are as good as possible, and so in that case, I might care most about like the mean squared error in prediction, right? And so yes, there is like a different focus on what diagnostics I might consider the most important, but it doesn't mean that we should be ignoring all of the diagnostics when you're doing a particular approach. You want to, again, think about this sort of holistically. Yeah. Why is it important? What relevant things does it tell us? And so when I run a model, like it's not going to answer these questions, right? my ability to answer these questions has to do with the interpretation of outputs of the model. And so think carefully about how you'd be sort of answering these things. And then know your audience. So think about when it's appropriate to be talking about, you know, specific diagnostic tools and so on, and whether that means something to the audience that you're speaking to, or is it more important that you just show them, you know, hey, these are the results, or like, hey, look how good my predictions are, or look how, you know, thorough I've been in my causal inference study, right? So there's a lot of detail that will go into developing the model, doing the analysis, and sometimes, and this can be difficult for some people, but like, sometimes the good work just has to go unnoticed, right? You don't need to sweat down the details of everything that you've done to every particular audience. Like, know when the right time is to talk about what things are coming out of your analysis. Yes, these are my sage advice from someone who's done this a lot. Okay, any questions about any of this? Okay, so you guys are all data analysis wizards now. Keep all this stuff in mind as you do your research in the future. Hopefully this is going to be useful to some of you. And if, again, you know, as kind of an applied data course, we don't get into theory on a lot of this stuff. Really, I'm trying to open your eyes to the tools that are available in the data analysis world. If you want to learn more about a particular you know, set of tools or approaches or methods in more detail, there are lots of classes that are offered here that can help you with that. And I'm also available as a resource if you want to learn more about this. Happy to help. Just shoot me an email. Okay, so that's it for lectures, and next week we're going to have our presentations. I'm going to make sure to get out a presentation schedule to everyone by the end of the week. Otherwise, what do we have left going on? Homework 4, the last homework is due today, I believe, at the end of class. Yeah, project report, or project presentation will be due Monday before class, and then project report is going to be due the week after that. I think Thursday night, because system will allow you guys to turn it in on Friday. So all those dates and deadlines are all available on Canvas, but just a reminder. Okay, thanks all.